Right, thank you. So today I'm going to talk about the 3D kinematics of the Orion Nebula Cluster, or the ONC. Specifically, it's about the mass-dependent kinematics of the inner cluster. So this is a work that has already been submitted and it's under revision, and I will present some of our results. So the main question that we're trying to answer in this study is how do star clusters form, or how do low-mass stars form in clusters like the ONC? So despite our knowledge on star formation on an individual basis, there's a lot that we do not know about star formation as a collective behavior. So answering this question helps us constrain the star formation theories. And the ONC is an ideal target for this study because it's one of the closest and massive star clusters from us. So there are multiple star formation theories explaining in the literature, and here's one example by Bonnell et al. 2008, which mainly involves gravitational fragmentation. And the fragmentation involves different types of fragmentation, including the turbulent fragmentation and disk fragmentation, which are proposed in previous works. But the general idea is that when the stars are forming in the cluster, in the gaseous regions, they're not only forming in the center here, which are the bright spots here, they're also forming in these filamentary structures here before they are before they infall towards the center. So one observable of this mechanism is that there, as you can see on the right, there is a downward trend between the velocity relative to the center of mass of each star, of the center of mass of its neighbors, relative to versus the final mass at the end of the simulation. And the reason behind this is that when stars are forming in these gaseous regions, if their velocity is too high, the high velocity will either eject them out of the gaseous region, which stops accretion, or it's because the high relative velocity between the star and the gas is simply too hard for them to continue to accrete. So as a result, we see a negative trend here, or put in other words, low mass stars are moving faster compared to their neighbors. And this trend is not only observed in that Bonnell et al., it's also observed in other simulations like Matthew and Federer 2021. On the top, it is the initial moment, as the early moments of a star cluster's formation, and we do also see this trend. But furthermore, they also observe that as the cluster evolves over time, this trend gradually dissipates away. And in the bottom, this simulation lasts for about 0.9 crossing time scale of the cluster. 0.9 relaxation time scale of the cluster. So this trend then disappears. So it is important for us to know that we have to observe a cluster that has not been relaxed yet for us to see this trend, which I will talk to more about the ONC, in the case of the ONC later. And we wonder if the stars in the ONC, especially low-mass stars, are formed in this way because the ONC happens to be concentric with a gas filament structure, which is called the integral-shaped filament, because it takes the form of an integral shape in mathematics. But yeah, the point is that in the left we have a column density map of the integral-shaped filament, and in the right is the ONC itself, taken by the WISE telescope. And then in the center we have a synthesized image. And as you can see, these two structures happen to sit right on top of each other. So that's what motivates us to answer this question and study the ONC. So in order to do that, we point the Keck Observatory to the very center of the ONC. As you can see in the left, we have a full view of the ONC, and in the right, it's a zoom-in view of the very center region of the cluster. And all the magenta circles in the very center is what we observe with NIRSPAC with adaptive optics or NIRSPAO. And all these sign boxes shows previous apogee RV measurements. And the amber triangles shows another optical RV survey conducted by Tobin et al. 2009, and the data is reprocessed by Konkel et al. 2016. And we are interested in the center because, as you can see, is because the center is the most active region of the star formation, and also most of the interactions are going on. So if we want to study, understand this cluster, the center is the most important area. And in this study, we're studying everything within this white dashed circle, which indicates a 4 arc-minute radius. And in the right is everything within this circle. And as you can see, previous observations are limited by limited spatial resolution and the nebulosity in the region. But with adaptive optics in the Keck and also in infrared wavelength, we are able to overcome this problem and obtain high resolution spectra. And here is an example of the spectra. The data itself is, probably can't see it pretty well, but it's in the gray in the background. And we modeled the stellar spectra using the Phoenix atmospheric stellar models using SMART, which is the Python package developed by Xu et al. 2021. And it's mainly done using Markov chain Monte Carlo method. And the modeled spectra is plotted in this red curve itself. And the blue curve shows the model with the telluric features. And in the bottom panel, we have the residual and the noise. And for this wavelength range of 2.29 to about 2.33 microns, we are mainly modeling the CO absorption lines, which are overplotted in the top. These are the lab CO lines shifted by the RV. And the stellar parameters modeled are listed in the right. As you can see, we are pretty high on precision of RV measurements. This one is about 23 plus or minus only 0.3 kilometers per second. So with this high resolution radial velocity measurements, we combine it with previous proper motion measurements done by the Hubble Space Telescope in Kim et al. 2019. So we are able to get a 3D kinematics map of the entire region. The arrows denote the proper motions, and the colors represent the radial velocity. And one trend that is hard to see by naked eye in this region is there is actually a counterclockwise rotation. And we can tell that by measuring the angle distribution between two vectors. Here shows the histogram of this angle. The angle is between the displacement vector of each star from the center, and the other vector is the proper motion. So if these two vectors are perfectly aligned, or 0 degree, then it means it has a sign of expansion, and 180 means it's contracting. And we do observe slightly more sources at around 0, so we conclude that there is a slight trend of expansion, which is consistent with previous findings. But more importantly, there are a lot more sources around 90 degree than minus 90 degrees. So that is how we tell there is a counterclockwise rotation trend. But with this kinematics map, we are in the right place to answer the question that I raised at the very beginning of this talk, which is, do we observe this negative trend in the ONC? And the answer is yes. So first of all, we obtain the stellar mass by interpolating the effective temperature using a few of the stellar evolutionary models, and here's one example from the Baraf model. And it does show a negative trend either in the best linear fit K, or a slope of the linear fit, or the Pearson's correlation coefficient R in the bottom here, and the red shows the running average. And we do observe this negative trend in all 4 different stellar evolutionary models. So the takeaway of this page is that low mass stars are indeed moving faster compared to their neighbors. But one might actually naturally ask, is this because of energy equipartition? And the answer is no, because first of all, the timescale, the age of the ONC is not enough for it to become relaxed. The age, I believe it's only 1/3 of its relaxation time. And another reason is that when we plot out, because energy equipartition describes the velocity dispersion as proportional to the inverse square root of the mass, which translated into a log-log plot, we should be able to see a negative 1/2 slope. But the measurement painted in red is clearly do not show this negative 1/2 slope. So we conclude that this downward trend is not because of energy equipartition, and it has not occurred in the ONC. And as I mentioned earlier, we can also measure the velocity dispersion, which is an indicator of the virial state of the ONC. So here the red values shows the 3D velocity dispersion, which is the root mean squared of the velocity in every direction, and then versus the separation from the very center of the ONC, or the trapezium. And the red one shows the measured values, and the black curve with the gray area shows what it should look like if the ONC is in virial equilibrium. And as you can see, almost all of the observations are sits above the virial equilibrium model. And it's also true for the overall value of 2.26 kilometers per second is greater than the equilibrium model's suggestion of 1.73 kilometers per second. So low mass stars in the ONC center are supervirial, and this confirms our previous finding of the negative correlation, because we can only observe the negative correlation in a supervirial cluster. And yeah, so here are a brief summary of this work. So we obtained high-resolution spectra and radial velocity measurements of the central ONC using near-spec with adaptive optics. And then we construct the 3D kinematics of the central ONC. And the most important takeaway is that low-mass stars are moving faster, which could be indicative that low-mass stars could form in the gravitational fragmentation way, which I described at the early pages. And some of other findings is that energy equipartition has not yet occurred in the central ONC, and low-mass stars in the ONC are not fully virialized yet, and the central ONC is also experiencing a counterclockwise rotation and weak expansion. 26 seconds left. Perfect time. All right. Thank you.